We've talked about one random variable, so now let's talk about two, pairs of random variables. So we have a pretty good understanding of how to deal with a single random variable, whether it's discrete or continuous. And so now we can study multiple random variables. So let's say we want to study x1, x2 up to xn, and the relationship or dependencies between them. Okay, so this is where things start to get interesting, where I have multiple random quantities that interact in some way, and maybe I want to use one to infer the other, to make predictions, or anything else. Okay, so here's the nice part about this generalization, that we can actually get most of the intuition that we need by focusing on the special case of n equals 2 random variables. And instead of saying x1 and x2, we're going to say x and y rather than x1 and x2. It's just more convenient. When we go up to n random variables, we will say things like x1 up to xn. But for now, let's just say x and y. And if we had 3, we would say x, y, and z. All right, so in general, keep in mind that we cannot think about y as a function of x and vice versa. Okay, so this idea of two random variables is more general than a function. When you have a function, you should think that there's one random thing, and then the other object is a distillation of it. Okay, so there's really just one source of randomness. Here there are two random things that might share something. So they might have some relationship or dependency, but a function will not be enough to capture it. Okay, so let's give some examples. So as an example, let's say that x and y are so x is the desired signal and y is a noisy version of that signal. And maybe x and y are the temperatures in Boston on 2 consecutive days. Okay, so this kind of captures the point. If I know the temperature on one day, I do not have a function that I can plug into and get the exact temperature on the next day. There's still some randomness, right? It's still quite complicated. And maybe x and y could be the ratings of a movie by two friends. So maybe they agree on a lot of things, but they have some points of disagreement. Okay, so there are lots of scenarios we can think of where it's useful to have two objects for modeling randomness. All right, how can we visualize this? Let's go back to our abstract sample space. And we're going to draw our outcomes in there. So I have omega 1, omega 2, omega 3, and omega 4. And now I'm going to draw the xy plane. Okay, and I have two mappings. One is x and the other is y. They both carry the sample space into the real line. And now if I look at how they're carrying the sample space together, I'm going to get these pairs. So I'm going to get x omega 1, y omega 1, x omega 2, y omega 2, x omega 3, y omega 3, and x omega 4, y omega 4. And by the way, some of these could have landed on the same spot. So you could have had any kind of mapping you wanted. Here I just drew them going to unique points. Okay, so this is how we should think about it. There's some abstract thing that we care about, like animals or cards or engineering or whatever, and then I'm mapping it into two numbers. Okay, that's two random variables. And the way we're going to deal with this is with the CDF. So this is something we've done before. We need the CDF to hold together or unify discrete and continuous random variables. All right, and a discrete random variable, we could use the CDF to get the PMF, which is an easier object to work with. And for continuous random variable, we could use the CDF to get the PDF, which is also easier to work with. So what we're going to do is we're actually just going to define the CDF for two random variables. And then we're basically going to forget about it, because when we deal with discrete, we'll get the PMF. And when we deal with continuous, we'll get the PDF. And this lecture will focus mainly on the discrete case, the next one on the continuous case. Okay, but still, let's define a joint cumulative distribution function. Okay, so the joint CDF, okay, for two random variables. So what we're going to do is say, take the CDF and now make this joint function, joint CDF. The notation for it is capital F of xy, and it's going to be of a pair of random variables, x and y. What it tells us is the probability that x is less than or equal to the value little x and y is less than or equal to the value little y. So formally, it's defined as the probability measure of outcomes that map to things that are less than those values simultaneously. Okay, this comma is an important little distinction here. So in this set builder notation, it just means that both of these conditions have to be enforced. if I want to think about two sets that I'm intersecting, I could write it like this. So I have the x that are less than or equal to x intersect with the y that are less than or equal to y. This is shorthand. And I could be even more casual about it. I could just write x is less than or equal to x, comma, y is less than or equal to y. Okay, and the comma means and. And this is something you'll see more and more as you get deeper and deeper into probability, that people feel comfortable to just use the comma to list out all the conditions that they want satisfied. But you should remember that if you need multiple conditions to hold at the same time, that's an and that means intersection. All right, what are the properties? I'm just going to list them. Again, we're not really going to use the joint CDF in problem solving, but it's good just to have these in mind. So the properties are going to be non-negativity. So you can't have negative values. We're going to have normalization. So if I go to infinity for x and y, I'm going to get 1. And I'm going to have that it's non-decreasing. So if either x or y increase, then f of x, y cannot decrease. If I take the limit of y going to infinity, I'm going to get the CDF of x. If I take the limit of x going to infinity, I'm going to get the CDF of y. This is called marginalization. Okay, we'll say more about that in a minute. The point is, if I set y to be infinity, then I'm saying I don't care what value y takes. This is always going to be satisfied. Now I'm just saying that x has to be less than or equal to some value, little x, and that's just the CDF of x. Same thing for y. If I take little x to be infinity, I don't care what value of x I have because it's always satisfied. And so I just have the CDF of y. Enough of that. Let's go to the PMF. So the joint probability mass function is going to be this object that we're going to define right now. And it's going to be the same as what we had before. So it's just a function p of x, y, and it's defined for a pair of discrete random variables, x and y. And it's the probability that x is equal to little x and y is equal to little y. And by the way, how do I know if the random variables are discrete? It's simple. I just check if x is discrete and y is discrete, and then I'm done. Okay, so then that's that. So how's this defined? It's just the probability measure of outcomes that map into these exact values at the same time. So it's the intersection of the set of x that map to x and y that map to y. And so the shorthand notation for that could just be that x is equal to x, comma, y is equal to y. Okay, so you can use any of these that you like. We probably won't use the probability measure one because that's too abstract and removed for our purposes. And honestly, we might usually use this last one, and we just have to keep in mind that comma means both conditions hold, meaning and, meaning intersection. The range, same thing as before, so r of xy, of a pair of discrete random variables, that's just a set of values that they're allowed to take. So it's the values where I'm going to see positive probability. So the values in the real plane where I see positive probability. And if you wanted, you could derive the joint PMF from looking at the joint CDF, but it's going to be a lot easier for us to just start out with the joint PMF directly. So we will not really use the idea of a joint CDF in terms of setting up problems. Okay, but you could. We're not going to do it. Let's talk about properties. And I know we're getting into a lot of definitions and a lot of things that don't seem immediately applicable. And the point is, this is stuff that's going to carry us through the rest of the course. So we're always going to be coming back to these ideas. I'm just trying to lay them out all at once. And then we're going to keep coming back and applying these ideas and gaining more experience with them. So it does seem like a lot, and it is a lot, but we're going to keep using these over and over until we get used to them. Okay, so we have, as usual, 3 properties: non-negativity, and we're going to have normalization. So if I sum over x and y, I'm going to get 1 for the probability. And if I want to know the probability that x and y fall into some set, I sum up over the x, y values that are in that set. Additivity. Okay, so those are just the usual properties that we see, probability axioms. But one concept that you've seen before, but we need to kind of give it its own name in this context, is a marginal PMF. So P of x and P of y. These are the PMFs for the individual random variables x and y. Okay, so nothing has changed. If I just told you it was a single random variable x, this would be its PMF. Same for y. But how do I get them from looking at the joint PMF? What I need to do is sum the joint PMF over the random variable that I do not want, and then I get the marginal. So if I want to get the PMF of x, I sum over y. the joint PMF. And if I want PMF of y, I sum over x. Okay, so I aggregate all the probability for all the possible values of the thing that I'm not interested in. The other thing to keep in mind is that if I tell you the marginal PMFs, you do not know enough to determine the joint PMF in general. Okay, so there are some special cases, and I'll tell you what those are later, but in general, the marginal PMFs do not determine the relationship between x and y. They just tell you the individual behaviors of x and y. Okay, so there are many different joint PMFs that would have the same marginal PMFs. Let's try to visualize this idea of marginalization a little bit. So what we're going to do is sort of abstractly visualize the joint PMF as a table. Okay, so I'm going to draw this giant table. There it is. I'm going to draw in x and y. And so these are the abstract values I can take. Let's say x1 up to xm and y1 up to yn. I'm just going to start filling out this table. And the values in this table are just going to be the values of this joint PMF function. And what they tell me are the probability that x and y take the value in that entry at the same time. Okay, that's it. So what I can do with this table is if I want to get something, let's say I want to get the PMF of y. So I sum up over columns. So I smash all the columns together, and then I'm going to get py1, and then py2, and py up to n, right? So if I add up all the values in a given row, which is kind of like smashing all the columns together, I get the PMF of y, okay? So I've gotten rid of x by adding up all of its values. Same thing for x. If I want to get x, I could smash all the rows together, okay? So I could get the PMF of x1, and then the PMF of x2, and so on up to xm, right? By smashing together all the rows, because I've gotten rid of y. And in the context of the table, the property non-negativity means I should not see negative entries. Normalization should mean that the table entries all together sum to 1. And additivity means add up the subset of entries that you care about, okay? So figure out which pairs of entries meet your conditions, and then add up the entries in those parts of the table. We'll see an example in a minute. Let's do another visualization. I can visualize the PMF as a plot, but I'm going to need a 3D plot to do that. So I painstakingly made this 3D plot for you, and I'm just drawing some arbitrary values here to show you what's going on. So the heights here indicate the probabilities, okay? So non-negativity here is going to mean that these are not going to have negative values, and normalization is going to mean that the heights add up to 1. Okay, so, and additivity, again, you just add up the probabilities of the things you're interested in. Not going to write that down. What if I want to get a marginal PMF? Well, the way that it works, let's say I want to get the PMF of x, I'm going to project along the x-axis, and that means I'm going to sum up over the y-axis, okay? And here I'm visually doing that. So you could go and check that all of these heights work out, that I'm in fact summing up the heights to get the heights of the x PMF. Same thing for y. I would sum up over the x-axis, which is kind of like projecting onto this y-axis, and I'll get the marginal PMF of y. So you can check that these heights actually work out to be the sum of the heights in each line. Okay, so that's a visualization of how I get the marginal PMFs from the joint PMF. And you can see that if I gave you the individual PMFs, there's no way you would be able to guess the shape of the joint PMF without more information. Finally, let's do an example. We'll come back to this idea of a table. Okay, I'm going to do just a simple example so we can get a sense for all of these concepts. So let's say I have x and y, and then let's say that x can take the values, or y can take the values 1 and 2, x can take 1, 2, 3. Probability of 1, 1 is a third, then 0, 0, then a sixth, and a third. Okay, so this is kind of the information I've given. And we're staying a bit abstract here just so that we can get used to what's going on. So this is a very simple example, but it'll help us get used to this. Okay, so this is the joint PMF specified as a table. What is the PMF of y? Well, I'm going to sum over the columns, smashing the columns together to get rid of x. So if I smash together all these entries, I get a third for y equals 1. And then the rest, it should be the remaining probability. And I see that I have a sixth plus a sixth, that's a third, plus a third, that's 2/3. Okay, so that's how I get the PMF of y. And that's just marginalization. I'm going to do the same thing to get the PMF of x. Okay, so I'm going to sum up, so I'm going to smash together the rows here. So I'm going to have a third plus a sixth, that's a half for x equals 1. And then a sixth plus 0, so that's going to be a sixth for x equals 2. And 0 plus a third, that's going to be a third for x equals 3. Okay, so that was simple, and that's the marginal PMF of x. Okay, let's do something more interesting. I want to know calculate the probability that x is less than or equal to y. Okay, now this is maybe beyond what we've done so far in the course. So this kind of jumps out right away as something new. And it's a little bit beyond what we've even defined in the properties, if you remember them from a few slides ago. So this is a little bit more than what we've done. The important thing to remember here is that anytime you see something like this, it's actually shorthand. So it's actually a condensed notation for some kind of event. And remember, events take the form of membership. So it's the set xy belongs to some set b. Okay, that's really what we're talking about. And we haven't specified what b is. That's what's implicit in this statement. So let's look and see what values of x and y satisfy this condition that x is less than or equal to y. Okay, so the first one that we can see is going to be 1, 1. When x is 1 and y is 1, x is equal to y, so that's fine. The next one we can see is going to be 1, 2. When x is equal to 1 and y is equal to 2, then y is greater than x, which is also fine. And the last one that works is going to be 2, 2, because again, they're equal. Any other values that I look at will have x greater than y, which is not okay. So those are the three pairs that make this condition hold. Okay, so I'm just going to now work out this probability to be the probability of membership in this set B. Okay, and so by additivity, I can just add up the values in this set B for the joint PMF. And so I'm adding up the table entries for 1, 1 and 1, 2 and 2, 2. And so I'm going to get a third plus a sixth. So I get a third plus a sixth plus a sixth. And that's going to be 2/3. Okay. So the important thing to remember here is that this probability measure always takes in events. So this is one place where this formalism is actually kind of useful to remember. It's that anytime you see some kind of shorthand about the probability measure is that it's really asking you to input a set. And so even though someone might have written down in a problem some kind of, expression. So let's say, probability of expression. What was expression? Here it was x is less than or equal to y. Well, really what they're asking for is the probability of the event, which is membership in a set, that is implied by this expression. Okay, so anytime you're a little bit confused by that, you need to just work out what that set is. Okay, and we did an example of that just now. Okay, more definitions. It means is you're trying to refine your probability model for x, but what I really think you should think of as an application is just you're given y, you want to make some kind of estimation or prediction of x. To do that, you're going to need a framework. And the framework we're going to use for these kinds of predictions going forward in the course is conditional probability. And so what we really need is the conditional PMF of x given the event that y is equal to little y, right? That we observe some value of y. And we actually have a framework for conditional PMFs in terms of even generic events b. But we're not going to use that as much. We're going to use this specific realization where we see the event that y is equal to little y. And so it's important for us to define notation that applies just to this special case. Okay, the conditional PMF of x given y, which we write as p of x given y, is just the following. It's the function which takes the joint PMF and divides it by the marginal PMF of the thing that we see, in this case y, and it's 0 otherwise. So it basically takes that value when the PMF of y is positive and otherwise it's 0. And the reason we have that PMF of y positive condition is just that we've observed y, so y has to be able to happen or occur, so it has to have probability that's positive. So that's just, as usual, we insist that the denominator is not 0. Okay, we can do the same thing in the other direction. We can define the conditional PMF of y given x, and that's again just going to be when the joint PMF divided by the marginal of x whenever the marginal of x is greater than 0, so we're not dividing by 0. Okay, so let's just check that this is true. So let's say that b is equal to little x. Okay, so it's the event that x is equal to little x. Okay, so then the conditional PMF is in fact the conditional PMF of this event b. Okay, and expanding that, that's the conditional probability that I see a value y given that I know that x falls into this set b, and b is just a single element, so it's x equals to x instead of x falling into b. And now from the definition of conditional probability, I have the intersection of these events divided by the probability of x whenever the probability of x is positive. And that's exactly the definition for the conditional PMF. Okay, so it's very simple, but it's really important for us to have our own shorthand for this idea of conditional probability because we're going to be using it so often. All right, this has all of the usual properties. So conditioning is just shrinking the universe, and it's still a valid probability mass function. So it has the same basic properties like non-negativity, both for x given y and y given x. It has normalization. So if you sum up over the variable that you're interested in, then you get 1. Okay, this requires a little bit of unpacking. So the thing to notice here is that despite the fact that the conditional PMF takes in both x and y values, if you sum up over x for this first term, you get 1. And if you sum up over y for the second term, you get 1. Because it's really the probability of a single random variable given that the other random variable has already been fixed. So now the only probability that's left is with the single random variable. The other one has already been realized. Okay? So it's important to remember that for conditional PMFs. I also have additivity. So this idea that I fall into a set B, given that I know that the other variable is y, I just sum up the conditional PMF over that set B. Same for x and y. Okay, so I just sum up over those elements. And I also have the conditional probability techniques that we developed before. So I'm going to have the multiplication rule. This one's probably the most important to remember here. It's that if I want to get the joint PMF and I have the marginal and the conditional, I can take their product. That's the multiplication rule. And this is what I mean by having enough information. So the marginals are not enough information to get the joint PMF, but one marginal and the other conditional is enough information. So if I know the marginal of y and the conditional PMF of x given y, that's enough. Or if I have the marginal of x and the conditional PMF of y given x, that's enough information. I also have the law of total probability, so I can write the marginal of x in terms of the sum over y of this way of writing the joint PMF. Same thing for y, right? So that's maybe a little bit less interesting. And then I also have Bayes' rule for flipping conditioning, right? So if I want to go between different conditional PMFs, I can use Bayes' rule. All right, and so the main thing to remember with that is that the conditional PMFs are not equal. So P of x given y is not necessarily equal to P of y given x. Okay, we're going to close out with an example. We're going to go back to our table. And we remember in this table, we already worked out the marginal PMFs. And I'm just going to ask us to compute the conditional PMFs of x given y and y given x. Okay, and so let me just remind you what those formulas are so that we have them in front of us. So conditional PMF of x given y is the joint PMF divided by the marginal PMF of y. Same thing for y given x, it's the joint PMF divided by the marginal PMF of x. And these are kind of condensed. We have to remember that we can't divide by 0. So I'm just assuming throughout that we're not going to do that when the denominator is 0, right? Then the conditional PMF is going to be 0. So just don't divide by 0 and get undefined. When the denominator is 0, then the conditional PMF is 0. Okay, So we're going to go ahead and just work out the conditional PMF of x given y as a table. I need 6 entries in this table because I need to calculate the probability of x for every possible value of y. Okay, so it's just like the joint PMF in terms of its representation. It's still in this table form, but I'm going to have different values because now I'm just dealing with the conditional PMF rather than the joint PMF. So I'm going to go entry by entry in the joint PMF, pick up each value, and divide by the marginal PMF of y for that particular row. For the first entry, I'm going to have 1, 1. So that's the top left entry in the joint PMF table. And I divide by the marginal PMF of y, which is a third at y equals 1. So I'm going to get 1. Then I get 0 from the joint PMF table. And again, I'm going to divide by a third. So I'm going to get 0. And finally, I go to the third entry on that row. I get 0. And I'm going to divide by a third again. And I'm going to get 0 again. So I filled out that whole row. Okay, now I'm going to the second row of the joint PMF. I'm going to pick up the entry for y equals 2 and x equals 1. That's going to be a sixth. Okay, I write that down. I'm going to divide that by the marginal at 2 for y, and it's going to be 2/3. So I have a sixth divided by 2/3, and that's going to be a fourth. We're going to repeat this calculation because I'm going to pick up a sixth from the next entry. And again, I'm going to divide by the marginal at 2. That's going to be 2/3. So again, I'm going to get a fourth. And finally, I go to the last entry. That's going to be a third. And I'm going to divide by 2/3 again, because that's the marginal at 2. And I'm going to get a half. So let's calculate it in the other direction. So I want to get P of y given x. Again, I'm going to pick up entries from the joint PMF, starting with a third, write it down, divide by the marginal of x now at 1, which is a half. Okay, so I get a third divided by a half, which is 2/3. Now I proceed downwards. I pick up a sixth from the last entry in that column. So I get a sixth divided by a half, which is the marginal at 1 for x. So I'm going to get 1/3 for this probability. Okay, now we're used to these calculations, so I can see that for the next 2 entries of the joint PMF, the 0 entries of the joint PMF, I'm just going to get 0 because I'm putting 0 into the numerator. So I'm just going to write that down. So this 0 here just becomes a 0 in the conditional PMF, and so does this one. So I don't need to worry about those. And now I'm going to go into the last 2 entries. So I'm going to go down to the entry where x is 2 and y is 2. So that's going to be a sixth. Divide by that a sixth for the marginal of x at 2. And finally, I take the last entry where x is 3 and y is 2. That's going to be a third. And I'm going to divide by the marginal of x at 3, which is a third. And that's going to work out to be 1. Okay, so the thing I'd like you to note here is that the normalization property means that the rows of this particular PMF, conditional PMF, sum to 1, right? Because I'm fixing the value of y to be something, let's say 1, and then I see 1, 0, 0. So that sums up to 1. Or I could fix y to be 2, then I see a fourth half, so that sums to 1. Because I'm getting a full probability model for x for each possible value of y. It's a little different when I have y given x because in that table, it'll normalize across the columns. So the columns will sum to 1. Because here what I'm doing is I'm fixing the value of x and then I'm giving you probabilities on y. So if x is 1, then y could be 1 with 2/3 and 2 with a third. That sums to 1. And if x is 2, then I get 0, 1. That adds up to 1. And if x is 3, I get 0, 1. That adds up to 1. Just to give a little bit of intuition before we close out, what this means in this last table here, the conditional PMF of y given x, is that if x is equal to 1, y is still not quite predictable because it could be 2/3 for y equals 1 and 1/3 for y equals 2. But when x is equal to 2 or 3, I know that y is always equal to 2. So that's just a quick interpretation of what I'm seeing from that table.